All right, well, welcome everybody. I guess I'll get back to this since the recording just started. So here we are on Friday. And let's take a look at what we've got for today. What I want to do to start is see where everybody's at in their homework. Because I know for those that missed the memo to do a certain number of things between Monday and Wednesday, that it's an awful lot of stuff to get done between Wednesday and Friday, along with the stuff that we had planned for homework on Wednesday and Friday. Now, while we're doing that, I'm hoping that you can shout out some questions that you might have had. And we'll do a quick recap on building circuits for anybody who has not done that before or maybe has questions. We'll talk about some of the other sensor applications, the cybersecurity tutorials, and then talk about lots of the stuff we have published in terms of the additional projects along with the cybersecurity and the more sensor apps. Then we'll look at products that are available, support, and say our thank yous, and that'll be the end of the workshop. Okay, so let's start by getting some thumbs up on how far you got. So how many of you finished navigation? And I need thumbs up. I need full participation here, and if you could click reactions and thumbs up, because I can't necessarily see. Okay, keep on clicking it too. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I'm on the second page. 12, 13, 14, 15, 16, 17, 18, 19. Okay,
15.
actually, okay, let's do this a little differently. Anybody who has not gotten through navigation, please clap. Hit the clap button. And I'm gonna just keep an eye out. See lots of thumbs up. Okay, so it looks like we are all through navigation. Now let's talk about the code examples. There were some code examples that I had you go through in slides. Was anybody not able to get through that? Go ahead and just hit the clapping thing if you're, we might set up some kind of follow-up Zoom meeting to help get you through it if you didn't. Okay, how about, let's see, and then navigation with, oh, that's the same thing. All right, now application to cyber.org. Did we all get through that? Let's just give some thumbs up. I want to see everybody thumbs up for this. I'm seeing the thumbs appearing. Excelente. All right. So there is an email that I sent you with that. All right, now how about the functions? How many of you went through and tried slides 90 and 91 functions? Thumbs up, please. Okay, I'm seeing a good amount of thumbs up. Oh, excellent. You guys are looking good. Great. How about making sounds? Did we get sound effects? Thumbs up, everybody. Okay, I see one clapping. Okay, that's pretty easy, so we can get back to it. Your thumbs up are looking good, though. Okay.
I just bent the little pegs and skipped on until I could.
Yeah. Okay, so go ahead and follow up with me in an email. Let's see if, we'll want to get your anything fixed that's not not okay with that. Blinking the light. How did we do? Everybody get through that?
Claps.
Yeah, I see a couple of claps. I'm gonna, I'll take questions about that. Let's thumbs up, thumbs up. Okay, it looks like we've got lots of folks. Now, building the Whiskers. How many built the Whiskers circuit on their robot? Looking good. I want to see all your thumbs up or clapping if you didn't do it. I need everybody to vote here. Okay. So I see a few clapping. Okay. So actually I see a few more clapping. So we'll want to talk a little bit about building, testing, and navigating by touch. How about the optional extras? Terminal communication. Anybody try it? Okay, I'm getting...
I tried, but it didn't work.
Okay. All right, well, that'll be important. We'll talk about that. Okay, so let's see here. I think then the first thing we need to do, because I saw a few clapping about the blinking lights and building circuits. So we need to go and just pay a quick visit to that. And let's see what happened. All right, so if you need to connect two electrical parts together, instead of putting their leads together and twisting them and maybe soldering them, what we have for that is it's called a breadboard. It dates back from when electrical prototypers used to grab a breadboard out of the kitchen and attach things to them and wire them together. And so now, even though it's plastic and you can't cut bread on it, it's still called a breadboard. And
it's actually from New York City, and there was a whole section of New York where they would buy radio parts and nail them to breadboards, and that became the World Trade Center. So before that, it was called Radio Alley. Yep.
Wow, that is really neat. Thanks for the factoid. I might try to include that in future articles. Now, the idea behind a breadboard is if you need to connect two wires or the leads of two parts together, all you have to do is find a row of 5 sockets. And then once you've picked a row, push in the 2 or more parts you need to connect together. Does that make sense? All right. Now, in addition to just the breadboard, we've got lots of things that you can connect to. Ground is the negative terminal of your battery pack. 3.3 volts is the same voltage that the microbit needs to power its system. 5 volts is the level that some sensors need. And then these P0 through P15 sockets are, you can plug into them and then use your microbit code to say, hey, check what's going on P7, or hey, take P12 and connect it to 3.3 volts so that the light comes on, or connect it to ground so that the light comes off. Then what we do is and this is in the email homework, is find these resistors, and you'll need to find one with the color code red, red, brown. That's its tendency to resist the flow of electric current. So if you connect a battery to this, it will only let so much current through based on how high its resistance is. This is a fairly low resistance value, although they do go down to fractions of an ohm. The omega is ohm. And this shows, okay, there's a color code over here that talks about the color of each bar on the resistor. And so we can check red is 2, and then we have another red for another 2. Those are the first 2 digits of our number. The third color bar is the number of zeros to add after the 2, 2. And then the fourth color bar is how precise the resistor is. And so for the sake of our tutorials, we always call out the color bars. So you can just go and fish them out of the bag in your kit. Then we have you take a light emitting diode or LED. These things, they work if you plug them in one way, and they don't work if you plug them in the reverse way. And so there's a longer pin that tells you, essentially we use that for reference when plugging it into the breadboard. And then this is from our tutorials. It talks about how a program using bot 12 write digital will, inside the propeller chip, connect to 3.3 volts, and that's write digital of 1. And if you say bot of 12 write digital of 0, it'll connect P12 to 0 volts, and the light goes off. When it's 1, the light comes on. It's a great lesson on binary. And what it does is it works on this circuit right here that the tutorial has you build a little bit more elaborate one with 2 lights, but the slide here has you build one with 1 light. And if you haven't done this, I think it's of maximum importance to try this out, make it work. And notice I called out the longer pin here. There's also a flat spot on the other side that if you end up shaving the pins to the same length, there's a little flat spot on the actual plastic case of the LED. So basically what you do is you're connecting one end of the resistor to P12, so you can send your 3.3 volts or 0 volts with right digital 1 or right digital 0. And then you're connecting the other end of that resistor, because they're in the same row here, to the longer pin of the light. Shorter pin of the light goes to another row, and in that same row there's a black wire. That's just a convention. We like to use black for ground, red for any kind of supply voltage, and then the yellow or blue for signals. So see how this wire is coming down to ground. Now, are we okay? Can I get, you know, if somebody's not sure if you still have a question in your mind about building circuits using these instructions, I definitely want to hear from you. Otherwise, we'll go ahead and move on.
Andy, I have a question back on slide 101.
Okay. Here we are on 101.
So on the bottom left figure, there's a blue wire that is connecting one side to the other. And
Yeah,
it
look
says,
at that.
because the jumper wire in the middle connects the two rows together, it's connected. Does it have to be a straight line there, or can that jumper wire connect to a different row and still be connected?
That's a good question. And the answer is it can connect to a different row. It's basically because these two ends are connected since they're both in this row, and these two ends are connected since they're both in that row. All the sockets on this row are connected. So this wire is connected, that wire is connected, and any other wires you plug into these empty sockets on these two rows are connected. If you took this blue wire, moved it up, took the yellow wire, moved it up to the same row, then you'd have, you know, the 6 additional sockets that are still unused, just on a different row.
Thank you.
Yeah, certainly. Thanks for asking. All right. So going back to our inventory. Let's see here. Making sounds, slide 97. So this is a nice, quick and easy one. You just basically find the little round disc that it's a speaker. You that visible? So this is what it looks like. It's got 2 pins coming out of the bottom, little hole on top, and you just go ahead and plug it in. You find the plus sign on the speaker. It's right there. It's hard to see in the camera, but then you just plug it into the board like so. And then what you can do is run a program like this for a nice little sound effect.
We just had trouble plugging it in. I can't speak for everybody else, but we got it in now. So.
Oh, excellent. Okay, good, good. Yeah, if anybody wants to do a hands up if you had the same issue, certainly want to hear. Was it that maybe the pins were too far apart or something?
No, it just I pushed it in and bent one of the pins, and then I tried to unbend it, and that made it not the right size, and I just kind of moved on.
Oh.
I got my dog to plug it in.
Oh, that's awesome.
But we got it now.
Okay, let's try this again. Flash. Well, that's interesting. I'm getting a syntax error from having pasted that code in. Okay, no module named Cyberbot. Oh, yeah. So look at that. So learn by my mistakes, folks. Remember to add the Cyberbot module to your project before you try to run it. And turn the power on. Oh boy, I'm having a banner day here. Let's try resetting it. That's unusual. Flash. Wow, no sound effects. Okay. bot of 22 dot tone of 3000 for the frequency, and let's do 2000 for the time. Flash. Still no sound. All right, let's try a different. I think it's worth actually watching me go through this because troubleshooting will have to happen in the class too. And so hopefully you all benefit from me bumbling around a little bit like this. Okay, so for whatever reason, I'm getting a syntax error on this one too.
Your batteries are good, Andy? Oh.
No, my batteries are good. It's that I forgot to add the Cyberbot module to this one too. That's why it's good to have that pre-written hex file to start up with. Just drag that onto your browser and you'll be much better.
On mine, once I put it in the one time and it's always stayed there.
Yep, that's good.
Okay, it's supposed to do that?
Okay. Well, every time you, if you put it in once and then never, if you go back to, okay, so I'm going to save microbit program right now, or let's say, let's see here, with, let's see, Cyberbot template. Okay, so we'll go ahead and save that, just to have it on hand. Now, if I refresh this, if I refresh my browser right now, and then look at the load save, we don't have it in there. And you won't have it in there if you restart your browser. But if you drag the template.hex, which in this case has the tone, then you'll have it in your browser.
Okay, so since I hadn't shut mine off is why it's continuing to stay there.
That's right. So
Gotcha.
be careful about
Okay.
that. And then you can just drag that from your file browser. In my case, I just dragged it from the downloads that were still visible here. So then reconnecting and flashing. Okay, did you hear that, everybody? Okay, so I basically just put the speaker near my mic so that you could hear it. And if I want to increase the frequency to say 4,000 and then reflash it, there it comes. Or we can go ahead and reduce the frequency, flash. And if you want a musical note, like here's a C7 2093, and we have a nice list of musical notes that you can work from to make your own music. Okay, so any more questions about music before I move on? Okay, so let's now.
I had a question, Andy.
Oh yes, go ahead. You're good.
It keeps coming up in these, and that one wasn't commented out. You had happybirthday.py at the beginning. In the previous one, you had soundeffects.py, but it was commented out. I did all of these without ever really including anything, I thought. Are those just references to where you've compiled some other stuff that you might have used but didn't?
Actually, it's just a comment with the file name. In other words, if we're doing this file, soundeffect.py, what we want to do is so we've got soundeffect.py here, and we can basically copy without the hashtag, paste it into the script name, and then save it.
Okay, that was making me think that there was a separate project file that you were thinking about including or something like that. I get it now.
Okay, yeah, and then you can also use the hashtag to say stuff like C7.
Right. But you've just included that as line 1, just in case for some reason the actual file name of the hex file or whatever gets changed.
Yeah, and it's for when we distribute stuff too. Like if we have a zip of all these guys pre-done for the teachers, they can know to look for soundeffect.py.
Okay. Sorry to interrupt.
No, that's a great question. Thank you. Any more before we continue? All right.
Yeah,
As
is
you
there a
know,
way to make it permanent that the speaker doesn't come out? Is it like just push it in and can you bend the leads over so that it stays in there?
you know what? It's not going to come out. Even I mean, unless you pull it out. If you're
Yeah.
concerned about your students potentially pulling it out, then yeah, it's not. There's not really a graceful way to do that.
Okay.
You could basically, yeah, put little barbs, you know, on the end of your speaker, but oh, you know what? You could probably get in there. See if I can find an empty board. All right, so here's what's below the speaker, right here. And so you could potentially put a possibly trim away some of the plastic and put a blob of solder there. I don't know.
I didn't realize there's a socket there. That's fine. That's fine.
Okay. Yeah, I'm kind of hesitant to suggest that because it's if you make a mistake, well, I guess you know, basically if you were to make a mistake and you're good with a soldering iron, you can basically just take this part off and solder it to the pads. You know, so you know, bend the leads around to the pads that this is resting on and solder it to those.
You could put something on, like use one of those metallic permanent markers and just put a mark on it. And that way you, when they hand them back in, you could just do a quick glance to see whether the gold thing is still there if you're afraid of them taking off with the speaker.
I was also wondering how resilient these cyberbots are. Like, are they intended for one use only, or can, when one class is done, take them apart and then have another class assemble and go through the projects?
Yeah, go ahead, Chuck.
Yep. So when I was in the classroom with these bots, I was using BoBots at the time, and I got my first set in 2011. And when I left the classroom in 2015, they were still running. I went back to check in 2017, they were still running. Microbits, you can literally have a toss and catch with them outside. Very resilient. Cyberbots, a little more fragile, right? But they're going to last for multiple years. My suggestion, though, is not to try and use a Cyberbot for multiple experiences per day. So if you have multiple sections of, say, a cyber literacy course, you should have a set of bots for each course so that you're not building a circuit during the class period and then having to take it apart that same class period so that the next student in the day can use it. Have a bot for class 1, have another bot for class 2 so that they can build their circuits and use them for multiple days of experiences.
Oh yeah, yeah, Chuck, I couldn't agree with you more. Basically, if students tear down their circuit and then try to rebuild it every day, they've taken up half the lab.
So would it work if you had multiple classes to have, you know, one class working on it in September and another class working on it in December, where they're like, are they reusable that way? Can I deconstruct this and rebuild it without too much damage happening to it?
You can disassemble it back down to a box of parts, but I mean, it's a good experience, but I don't know if it's valuable enough to go through the disassembly and reassembly process. There are other things you can explore with assembly of fine motor skills and, you know, in the classroom rather than taking apart this bot, especially if you're using lock screws and lock nuts and whatnot. I would recommend that once they're assembled, you leave them assembled. You can take wheels off, but don't take servos and battery boxes and circuit boards off. That's just my recommendation.
Yeah, I'm on the same. I'm on the same wavelength with Chuck. Basically, unless there's a goal of having that mechanical assembly learning experience, leave the bots assembled for one semester or for one term, whatever that's going to end up being to the next.
Andy?
Yeah.
What I do for different classes is I use a letter and a number. So I write right on the breadboard, A1, A2, A3. That would be the first class, B1, B2, B3. That way, kids know they have the right robot because they get shuffled a little bit.
Yeah, if they accidentally swap them, that could be a thing. Yeah, and sometimes having a bin for each student or student group's bot in a cabinet, I've seen that used periodically too. The circuit overlay board, if you have things that you need students to try, or maybe you want to have your circuits built up permanently so that you can just plug it in and say, all right, well, if you're concerned about the code, here I'll run my code. Gee, see, it works with the soldered together thing. Now we'll put your code in there, and oh, look, it doesn't work. So now we've isolated it to your code. Those are things that you can do with the circuit overlay board. You can buy several. There are even groups like ARRL that that's the American Radio Relay League, the ham radio folks. When they do courses with similar robots, what they'll do is they'll distribute some circuit overlay boards that have pre-built circuits on them for teachers to try in a short time frame workshop.
Yeah, if I can show real quick, I have a good friend, Matt Kinman, who built me this one. This is the television remote project. So again, just a.
Do you want me to should I stop my share?
No, it's just they see through the camera. It's just a small circuit board with the circuit soldered on. So it's always there. I simply plug in this overlay board and just add the code. And then I've got another one for my light seeker. And it's just the pieces are soldered in there. Nothing underneath, so nothing interacts with the breadboard, and you just plug this circuit overlay. Really great opportunity that Andy's presenting there. If you have any questions about that, we're happy to talk more.
I'm at school today, and I have all these little, they're for pictures, they're, you know, like photo boxes. And so I took all of my extra pieces and I put everything in one of these. They come in a kit. There were 16 of them, and they're in different colors. And so I use these with some of my circuit stuff all the time. I just put all of my pieces for my bot. So all of my parts now are in one spot. They're not everywhere. But
yep, dollar store or a little tackle box. You'll find those in the dollar store also, and little tackle boxes and sports supply stores.
You can also get it from Target or Amazon, and it comes in a little carrying case.
Yeah, these do. And they were on sale at Michael's for 16 of them in a carrying case for $10. So
yep,
yeah.
and you can also get ones that have little sub boxes.
Yep.
That's it.
It looked just like this, and that way it holds everything, so you could number per class period if you want each one of the kids for period 1 or whatever. So yeah, that's what I'm doing with all the micro bits and extra pieces and everything.
Michael's had them on sale for $10.
Cool.
Now, I'm not seeing, it says I'm screen sharing. If I
You're
stop
screen
the
sharing.
share,
Oh, you were.
okay.
We see ya.
All right, how's that look?
You're back.
Thank you. Now, can you see the little video clip that I'm playing?
Mm-hmm.
Okay, so this is the Whisker Bot. And with Whiskers, that's kind of the most basic example of using a form of electronic or electrical feedback in order to aid navigation. And so basically what's happening here is when here's a top view. See how the whiskers are connected to the little posts on the side, and then they come across and then out? Well, if I press on this whisker right here, can you see where I'm wiggling my mouse, everybody? Yes, nod heads?
Yep. Okay,
excellent. You press on this whisker, it presses against these posts that are sticking up out of the board. We're plugging little 3-pin headers like this into the breadboard, and then notice that everybody's in the same row here. So we have these 3-pin headers connected to this resistor that's going to 3.3 volts, And this 3-pin header is also connected to this smaller resistor, 220 ohm, and this is 10K. If you were to look up its colors, to P7. And so what the program does is it says, hey, what voltage do I see on P7? Is it around 3 volts or is it around 0 volts? And normally when the whisker wire is not pressing up against these posts, it'll be 3 volts because it'll see the 3 volts up here through this resistor. And then there's no electrical connection to 0 volts. But when you press the whisker, it presses up against these posts. It's actually connected to ground through this screw right here. And so what happens is then the program will see 0 volts on that IO pin. And that is shown in schematic form in our tutorials like this, where we say, okay, well, look, the switch is open. So the circuit can only see 3 volts through these 2 resistors. But when you press the whisker, it closes the circuit and adds ground to the party, which is 0 volts. And now the IO pin sees 0 volts. Any questions? Okay, so I'd like to give you guys a close-up of this because it's a really important tutorial for getting everybody started. Now remember, when you see a badge, there should be a link. And so that link will take you straight to the tutorial, and I'll go ahead and paste this into the chat in case some of you haven't been there yet. Let's see here. Chat. Paste.
Andy, I like the fact that you take all of those parts for the whisker setup and sell them as a replenishment kit. That saves a lot of time.
Yeah, and I promised to send you guys links to the replenishment kit on Wednesday. I have not done that yet, but it is still on my to-do list. So
Take care of it right here.
Oh, okay. So Chuck, there are 2. There's the small parts kit, and then there's the nuts and bolts kit and the circuit parts kit.
Yep.
Awesome. Thank you. I will still be adding it to the email, but all right. So when you're done, it's going to look like this. Let me see if I can give you a better close-up of that. All right, so here's the Whiskers bot. So see how this wire is attached right there? Okay, now right here goes to a plated hole on the board that brings us back to the ground connection, the negative terminal of the battery pack. And so right now it's floating out in space. It's not actually contacting the post. And so that's when this socket is having 3 volts applied to it from up here. It's going through this resistor and through that resistor, and it's just sitting there. That voltage isn't really running any current. It's just sensing 3 volts. Now, when I close the connection, when the robot runs into something, you see how it pushes the whisker against the wire? That's when all of a sudden the circuit is now changed so that it's 0 volts, that 0 volts is detected right here. And there's actually 3 volts now is driving some current through this large resistor and into ground.
Andy, is this around the screw or is it in the little teeny hole next to the screw?
Well, here, I'll take off the back screw right here so you can see.
Okay, because it's hard to see because there is another little hole right there.
Okay, so first of all, this is a plated hole. So see the plating here, this metal plating? That is what, everywhere on this board, you've got these plated holes. They all go to the ground connection of the battery pack by traveling in metal traces through the fiberglass board here. Now, when you connected this post is pressed up against that plated hole. And then the little hook end of the whisker is either up against the post, or it should be up against the post on one side and up against the screw on the other. That gives them a little bit of vertical clearance so that if I push on this one, it doesn't try to drag this one with it. Does that make sense?
Yes.
All right.
Thank you.
You're welcome. And once you've got it built, the robot application isn't going to, okay, so by the way, this picture is in the slide. I'm going to try to have it added to the tutorial. I see that it's not there, but we need a good little picture to identify all the parts. Then we do have this helpful drawing to show, okay, well, you've already got the screw and this standoff. You did those while you were putting together the main bot. So just undo the screw, put the little whisker hook in, and then retighten the screw. Once you've done that and you've built your circuit, you'll have this. And we talked about how the circuit works already. Now the next step is to test it. So on the left here, nobody's pressed, no whiskers are pressed. This little light here means the left whisker is pressed, the right whisker, and both whiskers. Okay, so let's go to the tutorial and try that out. So that's testing the whiskers. And so we always get everybody in the habit of testing before they try to make the robot go. It's really a key engineering skill, and everybody from hobbyist to engineers, they try to put together stuff that has multiple subsystems. And then when it doesn't work, it becomes really hard to troubleshoot your long program and you know, your many electrical connections. And so it's much safer to be using, sorry, I'm trying to navigate in my alt tabs. Oh no. Close. Okay. Sorry, I thought my computer rebooted. Can you all hear me? Okay, good. Whew. My screen went blank for a second. All right. So let's see. Let's go ahead and connect to my remaining bot. I just disconnected everybody. And then in this case, we'll paste in the code just for the sake of time, but I cannot strongly enough recommend the act of hand typing your code, because that is the way to have it really sink into your mind, and it also leads to experimentation. So we'll go ahead and let's see. Okay, so this is setting a pixel on the display. That's part of microbit, which Cyberbot brings along with it when we import Cyberbot. It's equivalent to saying from microbit import star followed by from Cyberbot import star, but Cyberbot does that for us, so we don't have to do it. So let's load that and then take a look at our Cyberbot to see if our circuit is working right. Okay, so when I bring, first of all, this is a good sign because I'm not pressing any whiskers against any posts, and the whiskers are not touching, and there's no light on. But notice when I press the right whisker, oopsie, I guess I was better off this way. Okay, this is the right whisker. It's hitting the left post, but notice that the program is adjusting for us and showing that the right whisker, it's bringing the light on and off on the right side. And then we've got our left whisker and then both whiskers. And one important thing to impress upon your students is that until all those cases work just like that, they're not ready to make the robot go, because it won't do what they expect it to. And it's a good experience with essentially the unforgiving or literal nature of electronics and code. Okay, so after that, we can go on to navigation. copy. And I'm going to talk a little bit about this code after we paste it in. Now, I should have saved my code, but I know I can get back to it pretty easily. So, all right, so the instructions say not shown to set your 3-position switch to 1. So notice I only have 1 light on, 3-position switches in 1. Okay, then we'll go ahead and load the code. And coming back to the video, I'll probably need to get some stuff out of the way here, and I'll follow the robot along as it does its roaming. Actually, I'm going to hold it up first. When I put you can unplug it now that the code's loaded, although probably better to test and just make sure that, well, so here are the wheels running. And I don't know if it's going to be visible, but the wheel did change direction. So I'll go ahead and try to follow along with the robot, or maybe we'll do this. Let's see here. Yeah, that looks right. Oh boy, that guy needs some centering. Now, one thing Whiskers cannot detect, of course, is a cable edge. That's a different set of sensors. But do you see how the whisker touches and it turns a little bit? Now, this definitely needs tuning because it's not really getting out of the way in time. So did that basically get the idea across of how it's working? We okay? Okay, just jump in and stop me if I skip something. Now, there's a few things I had in the homework to try out making functions. So each of these places where it says def is a function, and we have forward and backwards and right and left. And essentially the code doesn't really start till here. So anytime the script has def in it, it gets skipped. It's just basically the Python runtime makes a note that it has forward, backwards, right, and left as functions that have reusable code that your script might ask to use. So then we get to while true, and then these are the read digitals, which basically check to see whether there's a 0 or a 1 coming from the socket you have that whisker circuit plugged into. And then when you get something like if both of the whisker readings are 0, it means both of the whiskers are pressed. And so at this point, it calls the backwards function. Now, what that does is it makes the script go and find backwards. So the script jumps up here and says, okay, what do I have to do now? I'll set the speed of the left servo at -75, the right servo at 75, and we'll do that for a quarter of a second. And once it's done with its job, it comes right back to where it left off. And then it calls another function named right. So up here, right, will do another job.
Andy?
Yes.
Are those called subroutines that define backwards and forward? Would you call those subroutines?
If I were programming in BASIC, yes.
Okay.
And there's a difference, though. Let me get over to the real program here. Okay. See if I can find the little message that says I'm disconnected. Oh, that's kind of unusual. My browser's frozen. Can you guys still hear me?
Yep.
Okay, thanks. man. Um, Okay, I'm going to try to close the offending browsers. Oh, hey, it looks like I'm in business here. No.
What was the question? Can we?
Yeah, sorry about that.
I'm happy to take a look.
What? Yeah, can you repeat the question?
My question is, are those subroutines forward, backwards, left and right?
Yeah, they are like subroutines if you're programming in BASIC. The way they're written right now, yeah, they behave the same as subroutines because all you're doing is telling the script to go and find the code that has that label, do its statements, and then come back. But
okay, all right, thank you.
Well, the thing is that it can do more than just
And in this case, as Andy gets ready, the subroutines in BASIC that you might have used with the Bobot are stored at the end of the code. You'll notice here that they're at the top of the code. They're functions in this case, right? We're defining functions that are going to be used during the code, and all functions are stored at the top that I can call later on. So the DEF command, the define command, is going to set up those functions of forward, backwards, right, and left. But the thing that Andy's getting ready to say is kind of similarly with the Bobot, you can define variables and use them in those subroutines. We can actually pass values with functions that from the main code that are going to be used up in the function call up above. So some really cool functionality with the Python language inside of Microbit.
Yes, indeed. That is exactly what I was going to say also. Thank you, Chuck. Yeah, I know you've taught a lot of these, haven't you? All right, so here we have our code backup. And so yeah, first thing is you have to, before you use any of these functions, you have to add their code. And you can actually, if you click by the number next to them, you can even collapse them. So you can just see, oh, gee, I have functions that have these names, or you can leave them uncollapsed. And yeah, the thing is that I could add for example, I could say backwards for 1 second. And then in my backwards function, I could say, I could add a variable like duration. And then instead of using a hard-coded 250, I would use the variable. So in PBasic, I'll spell that correctly. So in PBasic, that's not an option for the subroutines for the basic stamp. But here, you can do stuff like that to really, and you could even add another one called speed. And then you could use speed here where we have 75 hard-coded.
Andy, I have a question.
Yes.
Could we put the functions like forward, backward, right, and left seem like they'd be commonly used functions, especially if we used parameters for speed and duration? Can we put those in a library and can the Microbit Python development environment include libraries of functions?
Totally. That's what's happening with Cyberbot right here. We don't have a tutorial for it, though. It's kind of on my list. So you could take these and then basically just, I'll go to another. So I can have my script right here, and all you have to do is name it. So we could say, you know, maneuvers. And then this time you'd save it as a Python script. So I'll go ahead and download it as a Python script, and my browser is going to warn me it's a little leery of Python scripts. But then you can say, I believe it's just plain old import maneuvers. I think from maneuvers import star still works actually. And then you've got to add it to your project just like you did the Cyberbot. So the or browse for file. And go find maneuvers. There it is. Okay. And so now, looks like I need to re-add Cyberbot too. Now I didn't, I made some changes that probably broke some code, but just for the sake of example, look at this, we have maneuver, oh no, maneuvers looks like it for some reason became our main file. Oh, it is our main file here also. So we'll call this Whiskers. No, it looks like it just opened it up. Okay, so I'll probably have to send you a little video clip about that as a follow-up. Are we okay with that?
Yeah, or could you put it in the presentation stuff?
Possibly, yeah. It needs a tutorial. It's been one that we've needed for a while.
Because that would make things a lot easier if they could just pull up something from a reference library like that.
Yes, absolutely, absolutely. Yeah.
Thank you, Andy.
Oh, glad to help. Okay. So how are we doing with Whiskers? Do we have any questions? Because I really want everybody before the weekend's over to have done that at the very least. Okay, you've got to have more than just navigation. We want to see some motion, the ability to respond to something external in the world. Okay. So while the gigantic Cyberbot workshop still loads, by the way, folks, we are going to also elect winners before the end of the session for the Cyberbot coworkers wins and fails. And it looks like my slideshow is back. All right, so there's lots more stuff you can do. Whiskers is just one example of the many things that are in our the Learn site. In terms of student activities and of course curriculum support for it. So these are some basic things, although once we get to dictionary, exception handling, and strings, these are more advanced basics for computer science-y type stuff or prep for the cybersecurity tutorials. But this top row here is nice rudimentary stuff. Then we get to some of the places you've already been, like the navigation, the build your Cyberbot. Here's the circuits tutorial, the Whiskers that we did. The next one is light. And so let's take a look at light following for a photosensitive robot. So this is another one with circuits. These are called photo transistors, and they conduct more current when they receive more light, or less current when they receive less light. And then the circuits that you build are not overly complicated here. But once you've built them, you can also write a script that that measures, quantifies the amount of light that's striking each surface. and then decides, okay, this one's getting more light, so I'll turn towards it, or this one's, or another way of saying it is this one's getting more shadow, so I'll turn towards the one that's getting light. So that's a pretty neat thing. And here is an example of it running. I'm torn as to whether to show this video. See how he changed direction with the flashlight. I don't know, was that a good enough shot, or would you like to see that? I can do that right here. So here is my lamp. And when I turn it on, see how I can lead my light following bot around. Now, you can also calibrate it so that it goes out the door. If you turn off the lights in the room and have light streaming in a door, now what I'm doing is I'm casting shadows in order to determine its motion. See how it turns away every time I put my hand over one of the sensors? So that's kind of a neat thing, and it's not a difficult circuit to build. And then there's lots of lessons that come along with it. For example, for those of you who want to use Ohm's law in your classes, the first thing we do is use a circuit that converts light to voltage. So this is the light to voltage circuit. And then later on, when we have so like here, for example, is the Ohm's law calculation that goes along with that, because the voltage across a resistor is equal to the current passing through it times its resistance value. And it's a basic electricity calculation that is commonly taught. Let's see. Any questions on that before I move on to the next example? All right. So the next one is infrared sensors. This circuit is a little bit more involved. Not much, but it does take usually a couple of tries in order to get all your testing right. So the first thing you're going to do, just like in the other one, is now remember the badge will take you straight to the tutorial. So now, instead of running up against a surface to detect that it's there, it's using those little black tubes or little infrared LED flashlights that are shining light out, and then the little boxes are infrared sensors, the same kind that we've got in a television set. So essentially, the little tube shines infrared light out. It also flashes it very rapidly, because this little detector right here is what you have in your television set. So when you point your TV remote at the television, if you have that kind of remote, or moving towards radio mostly, but if you have an old school TV with the old remote that you had to point at it, this would have to flash infrared on and off at 38,000 times a second. And if this sees it, it sends actually the same signal a Whisker would send to the microbit. And so it talks about that, and it walks you through step by step. Here's how to put together the little infrared light shield. And then here's the circuit, both in schematic form and in wiring diagram form. And then the all-important test. So essentially, here's some test code that you run to make sure that you're, just as we tested the Whiskers, this is testing the infrared. All right, so I'll just show you that real quick. Or well, you saw it. How was the video? Were you able to see the video okay? That the robot didn't have to touch anything and that it turned. Was that visible in the YouTube?
Yep.
Okay. So I'll go ahead and skip that then. Take a look at some of the kits. So over here is the line follower. Now, some of you today will have the option to choose this because you won one of the contests. So this is the line follower. And these are the QTI sensors that you go ahead and attach to the underside of your bot and to the breadboard. And then we already saw the rotating ping mounting bracket the other day. That's kind of cool. Go ahead and run this guy around for a second. So, and at any time that the sensor swings around and it sees an obstacle at a certain distance, it will go ahead and turn away from that obstacle. So the last two are not included. So the whiskers and the infrared are included in the kit. Now you can do more than just navigate with the infrared detectors. Another thing you can do with the infrared detectors, this is kind of like one of those Ginsu knife commercials, huh? Is that you can use like I said, it's a universal TV remote, and you can drive the robot around with the remote. That's one of my favorites. And another one that is one of my favorites is, okay, so let's look at the distinction here. First we'll look at the avoid obstacles bot. See how it turns away from any obstacle that it sees. It's adjusting away from the wall. Every time it gets close enough to see it, it turns a little bit more. Now, just by using a different program, you can instead demonstrate your ability with the force. And this is the robot you're looking for, I guess. Notice that what the script is doing is it's actually using the same sensors to measure the distance of the obstacle it detects, and it's adjusting the motor speed to try to maintain a constant distance for both sensors. And quick close-up of that. Do you see how as I get closer and further away, that as I get closer, there's fewer lights on the microbits, and as I get further away, there's more lights? Okay, so those are some of the things that you can do with your Cyberbot. The infrared and the light sensing and the whiskers you've all got in your box. The ping ultrasonic and the QTI line sensors are extras. And how about if we do the contest to see who won the extras? All right, I'm looking for the Cyberbot wins here. This looks like the Cyberbot wins. So I'll go through these quickly. Tidying up the wires. This is very nicely done. What she did was, what Cheryl did was she wrapped the wires around the post. Another way you can do it is pull the wires through and then tuck them underneath a servo. that's also a decent way to do it. Just make sure to run those wires through the hole in the center of the chassis there. Okay, so what's next? I see a lot of you in here. Cybersecurity radio data. This is pretty cool. So we have 2 robots, each connected to a different computer. And what he's going to do, I'll fast forward it, is he typed in 10 over here, and then this Cyberbot received it. And in this display on this computer with this Cyberbot, as he types in over here, this Cyberbot's transmitting it over radio to here. And so he typed in a countdown of 10 and a message of awesome. And so it's counting down. And then at the end, it displays awesome. So this is one of the examples from the cybersecurity tutorials. And I'm assuming you couldn't hear the audio on that, so I went ahead and narrated for you. This is a great one where we've got links for a well-known musical score, so it actually plays the beeps. And again, we can't hear that, but it's every time it beeps, it also turns on the light. And the great thing is that Debbie included links to these. And then this one is really cool because you tap keys on the keyboard to get different notes. And so each time he hits a key and then enter, he gets a different note. And so this has a video clip, the description, and the code if you want to try it. Here we have another one where basically the challenge was getting it calibrated to stay still. Congratulations, Matt, you made it. And then from Cornelius, we have the shark fins. That's if you use the high-speed servos. You might need those for stabilization. And let's see, Jamie posted this, and we don't have access yet, Jamie. But let's see here, getting the parts put together properly. And the winner is, I'm going to search around for a little bit, the keyboard piano. Why did I choose this one as the winner? One of the most important things is this is what you want to get your students to turn in, is something that anybody can repeat. So we have, a demonstration on the YouTube video of what it does and how to do it, the code to try it out, and then an explanation. And so this is there were several good ones, but because of the fact that this is very complete and repeatable, I wanted to make this the winning entry. And so that is my choice. Now on fails, we have screw in too tightly. I appreciate this fail, Cheryl. It's a good warning to just use a very delicate touch when tightening the battery screws. Let's see here. Oh yes, and so this was the one where Lori thought she had to get the servos at a particular angle using the screws, and no, you just want to get them to stop. Here we have the metal screws were put in initially. So be careful about that and make sure to check your students so that they haven't done that. And let's see here. Oh, so this was a construction error, and it didn't make the electrical connection back here. So let's see, out of these, I'm really having trouble choosing this one. See if okay, so this is supposed to be turning right. Matt, if you still need help with that, let me know. I'm going to award the biggest fail to Lori for trying to get the servos to a particular position instead of getting them to stop. It's an excellent mistake that students will make, and so that's the biggest thing about the contest is that we want to essentially enhance the what you're able to offer in the classroom. So keep an eye open for this one. So we have Debbie and Lori, and then I think for the coworker, let's go ahead and just okay. So I'm not in the running. That's Hazel, my cat, who's always helping me out. Mark also has taken himself out of the running because he's received sample parts from us already. Thank you, Mark. That's very gracious. So here is Penny. And here we have Hank the Tank, who gets very curious when the robot starts moving. Squaring off with Gentle Giants. I love the name from Cheryl. Fortunately, he didn't eat the robot. He just went by it. And it looks like this one got the dog's attention. They were snoozing before, but once he started running it, the dogs really took notice. And that is Tudor and Pepper. Okay, then we have
Brittany's this one.
okay. Thank you. And Brittany has a number of coworkers, each of which is investigating the robot as it does its thing. Nice job on the Whiskers too. And then we have 3 wonderful helpers.
Yeah.
Okay, so let's, I really can't decide this one, so let's go ahead and take a vote. Okay, so let's count thumbs up for Gentle Giants.
I got 2.
Okay. Thumbs up for being woken up. I see 1. Any more?
It's a lingering one.
Okay. Oh, that was okay. Thumbs up for the whole kit and caboodle. I see 3, 4. Wow. Okay. 1. Whoa. Right on. How many? Let's see. 2, 4, 6, 7. 8, 9, 10, 11, 12.
8. Oh,
Okay.
9.
All right. And then the 3 wonderful helpers.
I got 4.
3, 4, 5. Okay. And Avery and Jessie. Those are good puppies. I have to get that voice every time I see dogs making those face. We got a couple thumbs up for that. So who was the 9 again? That was
The whole kit and
that was
caboodle.
the whole kit and caboodle here, Brittany. Is that right? Congratulations, Brittany. So we have Brittany, Debbie, and Lori. So folks, email me and we'll send off your, I think I actually have your, yes, well done everyone, I agree. So, okay, so that takes care of the contest. Congratulations everyone, and thanks for participating. And what do we have next? I did projects, so I'll show you briefly about cybersecurity tutorials. I usually spend a little bit more time on this, but this is my first time through these tutorials, and I'm still trying to get used to the pacing. So we'll just show you, kind of give you a quick little talk about it briefly. Okay, so there's this is where we're at. Brute force was supposed to go up yesterday, but our editor is still working on it. She's almost done. Brute force is going to come live. My guess would be today. No, she's off today. Early next week. It was planned for today, so I could say, hey, look, brute force appeared, but it's not ready yet. So about cybersecurity, let's see, let's take a look at the, I put links to all the tutorials on this slide, and, but I think I'll just go to learn, not LAR. Learn.parallax.com, and then follow the Cyberbot link. So as far as cybersecurity goes, the prerequisites that are listed in the early cybersecurity tutorials are computer microbit talk is the main one. And then dictionaries, exception handling, and strings and characters are also come into play. Computer microbit talk is a lot of fun. And this is one that we can use a single microbit, and I'll just show you a quick example. This is an example of using the terminal to enter a countdown. And I see an error in this code that's a little unfortunate. Where is the countdown? Okay, there's the calculator. And here's the countdown. So I'm going to paste this in, fix the error first, and then paste it in your see here. Okie dokie.
I have a question just about the learn.parallax.com and cyber.org. Does the curriculum on each site complement each other? Do they replicate each other? I mean, I'm not quite sure about the two different websites.
That was cyber.org versus Parallax?
Yeah.
Okay, so cyber.org, I'll let Chuck talk about that in a minute. The main difference is that the Parallax curricula is more targeted at using electronics to invent. That's our history. That's our biggest emphasis. And of course, we like to play with robots, and we like to have fun and learn. And what we do is we pepper in as many curricular check boxes along the way as we can. And so with the now the Cyberbot is done in conjunction with with cyber.org. And so that is going to be a little bit more to their standards and a little bit less to our style. And so then when we switch completely over to cyber.org, there's stuff that goes well outside of the Parallax products. So the learn.parallax.com is for, the robots and the kits that we make. Now I'll pass it to Chuck for a description of the differences at NYSERC.
Yeah, thanks, Andy. So, so Andy and the Parallax environment is global, right? So they serve partners that are outside of the United States, and hobbyists and makers and like you said, inventors. The cyber.org content is tailored specifically for K-12 education in the US. So we have similar lessons, we have similar content in the areas of robotics, but we also have elementary, middle, humanities, liberal arts, a wide variety of other content areas. But when you're talking about things like cyber literacy, that course is based on the book that used to ship with the Bobot. So every project that they're working through in that book, we turned into an interactive project-based small group instruction opportunity for the classroom. Similarly with Cyber Literacy 2 and some of our other robotics-based courses, they're using the robot to enhance the curriculum in the classroom. We have a physics course that uses the Bobot, and we talk about electricity and magnetism as we turn the bot into a hoist and a winch. We're measuring voltage and we're calculating work, and then
I love that one, by the way.
Yeah, we're comparing it to kinetic and potential energy. I mean, fabulous connections where we might have made that with a textbook in the past. Now we're doing it with a Bobot. So that's my 2 cents on the difference.
And my best recommendation is to mix and match. pick whatever you need for your class. If you're a US educator, you've got access to all of the free curricula at NYSERC, which goes well outside the inventing with electronics realm, as well as within it, using a variety of robots, most notably the Cyberbot. Okay, so before we run out of official time, and I'm going to talk a little bit more about cybersecurity after the official end, but since we're coming up on the hour and a half point, I just want to make sure to hit a few more items that I want you to know about that are in the slideshow. The first is products. So if you need to get a Cyberbot for your classroom, here it is in all its Cyberbot glory, both constructed and the parts you get in the box to start with. Now, that kit, if you buy one, it's $219. And once you get to equipping a classroom, it's $197. Now, there is also a box set, and this is kind of interesting. Oh boy, I didn't update this price. I'm sorry about that. I don't know if this is the right price. Don't want to be false advertising here. Okay, so what I did was I copied the part number and I'm pasting it into the search field at www.parallax.com. And oh, I didn't do the, I don't know why I did 32700. Oh, look at that. The part number is wrong too. 12 pack. Let's try that. Okay, here's the Cyberbot 12 pack. Now, if you go through the math on this, see, so the price of 12 Cyberbots plus enough rechargeable batteries, battery chargers, QTI line follower, ping mounting bracket, TV remote, it adds up to a little higher than than it would if you were just buying the Cyberbots alone, but you also get a lot more material, and that costs just south of $3,600, so $3,595. And again, you get 12 Cyberbots where you've got enough batteries to run your Cyberbot that are rechargeable. You've got the battery chargers, the add-on kits that we made as prizes, and TV remotes as well. So, so even though, you know, just depending on how you want to do things and what your budget is, you might end up being more comfortable with one or the other as far as, you know, gee, do you just want to equip your class using the quantity discount of say 20 plus at $197 per kit, or do you have enough budget to go all out and get a full classroom set that also supports additional activities? Like, oopsie. Well, you saw it, right?
And was there one, Andy, without the microbit, if you already had microbits?
That is a great question, and the answer is yes. So, so I'm on the with microbit page, and here is the without microbit. There's also the micro, see, there's the Go bundle, which is an additional microbit if you want to do the cybersecurity stuff just on your own. Just grab another microbit. It's under $20, so very good deal. Here is without the microbit, and you do see some savings since you're not paying for the microbit. And so these, the onesie and quantity prices are all slightly lower.
Cool.
All right. Now, the Cyberbot is one of a variety of robots. The Bobot was the original. That's what we got everything started with back in 2000. Actually, summer '99. I remember because I was an intern and I was really amazed by it when our mechanical engineer set it down and had it do its thing. This was very popular, and when the Arduino came out, we made a board that you could plug the Arduino into and do all the same things with the that you do with the Bobot with the Arduino bot. And then when the microbit came out, and this is cyber.org's brainchild, and so they came to us to design and manufacture it, which we did. And I say that as though it took a couple minutes, but it was quite the endeavor. All right, so So you can, if you have bots or Arduino bots, you can also just get the part that rides on top, because that's really all that differs between these three. So for example, if you have Cyberbots and you want to also use the Arduino on top of it, you can just get the parts that ride on top, because the motors and what's underneath are basically the same. The activity bot is slightly different. It has a different set of motors, but there's also upgrade kits for this. This one has cool motors that know each servo knows where it is rotation wise at any given moment. And so it automatically straightens out its path of travel without any adjustments to the code. You just tell it, hey, I want to go this fast or this far. This slide is very important. I would recommend copying and pasting this information and having it ready. We have an educator hotline, and you can call that. It's open 12 hours a day, and the number's right in here. It is also on our website, education@parallax.com for email. If you're wanting to buy kits, we have a sales line and email. And then there are discussion forums and Facebook groups, and they're all right here. Now for some thank yous. First off, hey guys at cyber.org. That would be during this session, Chuck, Josh, and Matt in alphabetical order. We really appreciate everything that you've done for the design of this, for the initial drafts of the cybersecurity tutorials, for coming and working with us, both on the hardware design of the Cyberbot and the tutorials, and of course today. And you, various members of the staff have been doing flight control and breakout rooms the whole time. So can we get everybody to click the clapping reaction for Chuck, Josh, and Matt? I think I'll do that too, if I can find my clapper. Ah, jeez.
We're thrilled to have a bunch of you to call new friends. So thanks, Andy and Ken, for hosting and setting these up over the summer. The least we can do is provide everybody with a bot, and again, give away everything we can do with curriculum and helping you guys in the classroom. So whatever it takes to, again, raise a level of conversation in the classroom, expectations of students in the classroom, and also make them aware of all the cyber opportunities that are available to them after they graduate and leave you for bigger and better things. And thank you later.
And you guys are great. You guys are great. This is just fantastic.
And so we will have future events coming up. You're welcome if you want to, go through this a second time. You've already got your Cyberbot. We can definitely add you into the Zoom. And then nicer. Eventually I'll get this. Cyber.org will have events coming up too. Chuck, do you want me to navigate to a particular page to show where to look for events?
Yeah, I'll paste the Eventbrite link. So everything is on our cyber.org page under events, or you can go right to Eventbrite.
Andy, I'm sorry, quick question.
Hey, Andy.
Yes?
Real quick.
Quick question. Can you help us understand about virtual? I know on Monday we had gone over the opportunity to send these Cyberbots to different households while we're virtual this semester, that kind of thing. Can you maybe just help us understand a little bit about the virtual classroom teaching this curriculum?
Well, essentially, if you are doing a virtual classroom, you'd be doing something like Zoom or whatever your school's chosen platform is to meet video-wise with the students. Then hopefully you've got things like a computer with a webcam and a document cam. Hopefully the kids have, say, Chromebooks or Windows machines, just something, Chromebook, Windows, Mac, that they can write the program on. The important thing about the Cyberbot is that you don't have to install anything. So there's no IT required involvement. When you plug in the Cyberbot, it just shows up in your Windows file browser, Windows E. So here's my Windows Explorer, and basically there's my microbit. And then this is just a normal website. So as provided your school hasn't locked out microbit.org, which I can't imagine, then your students, we drop ship the robots after you provide us with addresses of where to ship. And then the students can start working through the tutorials. We supply you with, this slideshow resource. We supply you with the learn.parallax.com student tutorials, and then NYSERC, cyber.org has additional ones. So you can, for example, say, okay, well, I want to go all the way through cybersecurity. And so we can look at, after a certain amount of time, you'll end up being here in the encryption. I hit the wrong thing.
So Andy, are the students buying, like the parents buying the robot, or are they like leasing it or renting it from you, or
okay,
what?
So in this case, my understanding is that if the school's paying for it in a single PO, then we have the option, we make the option available to ship them to each student. Now, another thing is, if the students have budget, yes, they can just each one go to the Parallax website and get their own Cyberbot. And then, of course, there's the third option, which is to just simply order the Cyberbots as a normal PO. And during the event where the parents come through, and if they're doing this all from home remotely, there's usually at certain times where the parents come through and they pick up their various books and packets and et cetera that they need from the school in a procession of cars. And so another item would be to give them the box with the Cyberbot in it.
Because that's the only way I could see getting them back.
Yeah, so you will need to get them back if you and that part is going to be however the teachers do it. There will probably be a day at the end of the term where the parents drive through and drop off their books and any other materials that are not reusable. Let me try that cybersecurity again. Encryption intro. Here we are. So encryption is kind of cool.